today. So it is my pleasure to introduce our speaker for this afternoon, Dr. Bob Scherrer. He recently stepped down from chair of the Department of Physics and Astronomy at Vanderbilt University, where he was chair for 13 years and 7 months, approximately cosmological timescales, as far as being department chair is concerned, I think. His research is in large-scale structure and CMB. More recently, he's been working on dark energy modeling and Big Bang nucleosynthesis. He has written a quantum mechanics textbook and blogs about science and science fiction, and also has some published science fiction short stories. And today, he will be telling us about the primordial lithium problem.
Okay, thank you. Thank you for allowing me to give a talk here. And I want to tell you today about the primordial lithium problem. What this boils down to ultimately is that the fact that while Big Bang nucleosynthesis is in fact one of the pillars of modern cosmology, it has a problem. It gives excellent predictions of the primordial deuterium and helium-4 abundances, but it fails badly when it comes to lithium-7. And this failure, and I'll discuss it in a bit more detail in a minute, it's called the primordial lithium problem. Now, you've all encountered lithium in your everyday life. I actually discovered a rod of lithium in my car at one point, metallic lithium, but of course it's found in batteries, it's found in pharmaceuticals, and there's an interesting connection between the pharmaceutical use of lithium and the cosmological use of it. So if I forget to bring that up at the end of the talk, please remind me. What's not as well known is the fact that certain soft drinks, of course, were thought of as medicinal in the early 20th century. Coca-Cola is famous for having cocaine in it. But after doing a little research, what I discovered is that 7-Up had lithium, I think it was either lithium citrate or lithium carbonate in it until the late 1940s. It doesn't have lithium in it anymore, but it's undoubtedly why they use this slogan, nothing does it like 7-Up. Now, the 7 actually is in no way related to the fact that it's lithium-7. That's a bit of a mystery where that comes from. But clearly the up, now you know why it was called 7-Up. The outline of the talk, I first want to go through standard Big Bang nucleosynthesis. I apologize to those of you who are deeply familiar with this subject. You can cruise the internet on your cell phones while I'm doing that part of the talk. But we'll go over what the standard model of nucleosynthesis looks like. Then I want to talk about why there is a lithium problem. What is the nature of the lithium problem, and why do we actually take it seriously? And then finally, I'll talk about possible solutions. And this is a very interesting subject because it includes overlapping fields of stellar astrophysics, nuclear physics, and cosmology. So I'll talk about first the astrophysical solution, which is really one of the observations are wrong. I'll talk about the nuclear solution, which is the calculation we're doing is wrong. And then finally, I'll talk about physics beyond the standard model, the speculative solution. And I'm going to spend the most time on part C, not necessarily because it's the most likely, but because it's the most fun and interesting, and also because I recently wrote a paper on it, and no seminar or colloquium would be complete without the speaker shamelessly promoting his own work. So I'll be doing that at the very end of the talk. So standard Big Bang nucleosynthesis takes place at a temperature of about an MeV down to a tenth of an MeV. And so to remind you how to rescale between energy scales and temperatures, an MeV in the early universe is at a temperature of about 10 to the 10th kelvins. And a tenth of an MeV when nucleosynthesis ends is at about 10 to the 9 kelvins. At these high temperatures, there's a thermal background of protons and neutrons, which are non-relativistic, photons, electron-positron pairs, and 3 types of neutrinos and antineutrinos. And because the energies are high enough and the interaction rates are high enough, the neutrons and protons interconvert via these weak interactions. So you could have a neutron plus an electron neutrino gives you a proton plus an electron. You could move the electron over to the left side and turn it into a positron, move the neutrino to the right side and make it an antineutrino, so you have this interaction. And then finally you have standard neutron decay. Neutron goes to a proton, an electron, and an antineutrino. And I left the charge off the electron there. But the reverse reaction can also take place in the early universe. You can have a three-body reaction where these things go back and give you a neutron. And because everything is in thermal equilibrium, Herr Boltzmann tells you that the ratio of neutrons to protons then is just a negative exponential of the mass difference between the two particles divided by the temperature, where I've left out the Boltzmann constant. And this equilibrium favors the lighter particle, which of course is the proton. It's an interesting coincidence that the difference in mass between these two particles, the neutron and the proton, is about an MeV, and that's the energy scale at which these processes are in thermal equilibrium. If they stayed in thermal equilibrium, then this ratio would be driven to 0. You'd have nothing but protons, and there would be no primordial nucleosynthesis. This would probably actually have no effect on life at all. We would still be here. We would be pretty much the same as we are now. It would only affect cosmologists, because I wouldn't have been able to write about a dozen papers. But other than that, it doesn't have any deep effect on us. But this is not what happens. This ratio doesn't get driven to 0, and the reason is that you have only a limited amount of time for these reactions to take place. A temperature of about an MeV is about a time of about a second. The universe is cooling down, and the rates for these interactions multiplied by the age of the universe drop below unity, which means that a given neutron or proton has a probability less than 1 of being interconverted, and we say that these interactions freeze out. You get a fixed ratio of neutrons to protons. But it's not entirely fixed, because you can still have free neutron decay. So all the interconversion reactions stop, but neutrons can still decay, and they do continue to decay down to a temperature of about a tenth of an MeV, or about 1 billion degrees. And at that point, you get rapid fusion into heavier elements. You get thermal equilibrium abundances of the elements that are high enough that you can start doing rapid fusion. And what you end up with at the end of Big Bang nucleosynthesis is a universe that's about 75% hydrogen, about 25% helium, and then trace amounts of everything else. It turns out actually those trace amounts are really important. We'll see that that's actually one of the most important things to come out of Big Bang nucleosynthesis. And in particular, you could make the atomic number the mass 7 elements by either a helium nucleus and a tritium giving you lithium 7 directly, or a helium nucleus plus helium 3 giving you beryllium 7, and the beryllium 7 then decays later on to give you lithium 7. So I put these reactions down because we're going to want to revisit them when we talk about how much lithium there ought to be. And by the way, although most of the helium in the universe is made in the Big Bang, none of the helium in your helium balloons, unfortunately, comes from the Big Bang. That all comes from Texas. It's mined underground. Helium escaped from the Earth's atmosphere ages ago, of course. You could tell that by releasing a helium balloon. That's where all the rest of it went. As you know, helium is produced from radioactive decay, and it collects in certain geological formations, and mostly in the United States. And that's where we get our helium from. So, oops, wrong button. Let's make sure that doesn't happen again. Here's a graph showing the evolution of these different elements as a function of time. So on the vertical axis, you basically have the abundance, what's called the mass fraction. That's the total fraction of a given of the baryons in the universe in the form of a given element. On the right-hand side, you have the temperature going down. This is an MeV, as I said. This is when nucleosynthesis ends. And on the top, we have the time measured actually in units of time. So this is 1 second, and this is 1 minute, 5 minutes, up to an hour. And you can see that what happens is initially all you have are neutrons and protons, effectively. They start to diverge with the neutrons being less abundant than the protons. And then when you get down here, there's rapid buildup of everything else, and you get rapid production of helium-4 up here. The deuterium starts to build up, and then it gets burned into heavier things. So deuterium is kind of like the carbon monoxide of the early universe. The only reason we have deuterium is because we don't have complete burning into heavier elements. Deuterium is very fragile, but you do end up with a mass fraction of about 10 to the minus 5 in deuterium, and that turns out to be very important because you can't make deuterium anywhere else but in the early universe. So this 10 to the minus 5 mass fraction of deuterium is very important. Helium-3 and tritium get made in comparable quantities, but I'm not really going to talk about them very much because they're hard to get a handle on in terms of what we think the primordial abundance is. And lithium-7 and beryllium-7 get made down here in much smaller quantities. And then lithium-6 is even smaller quantities as well. So I'll mention lithium-6 later in the talk, but it turns out to be produced almost at an irrelevant level in the early universe. So the game that we play is that we calculate the mass fraction of helium-4 made in Big Bang nucleosynthesis. We calculate the abundances of deuterium and helium-3 and lithium, but since this is astronomy, nothing can ever be consistent. So we use the mass fraction to measure the helium-4. That is the total mass of helium divided by the mass of baryons in the universe. But then for these other elements, we calculate their ratios relative to hydrogen because that's the normal way to observe them. And then, of course, we compare that to the observed primordial abundances. And this is where the problem starts because, of course, we don't observe the primordial abundances. We observe the abundances today. So we want to get some method of determining what those primordial abundances are before we compare to the predictions of Big Bang nucleosynthesis. This is a plot from the particle data group of the abundances of elements as a function of the baryon to photon ratio. And you can, at this point, I'll come back to this plot in a second, but I just want to give you the general qualitative behavior. As you increase the baryon density, the matter density, along the horizontal axis, you get more helium, which is what you'd expect, because the nuclear reactions go faster if there's a higher density of matter, and so the helium abundance goes up as the density goes up. The deuterium abundance actually goes down as the density goes up, and that's that carbon monoxide effect I was talking about earlier. That is, the only reason we get any deuterium at all is that there's not enough time to burn it all into heavier things. So as you burn more efficiently at higher densities, you get less deuterium. The lithium is a fairly complicated behavior, and the reason it's complicated is because this actually represents two different elements. Down here, you've got lithium-7, and that actually gets destroyed at higher densities by an incoming proton reaction. And then up here, you've got beryllium-7, which increases in density as the density goes up. And that's why you get this characteristic trough and then an increase. And I'll talk about this vertical line in a second. First, I want to talk about how we infer the primordial abundances. Deuterium is really the one element where we've made tremendous strides in the last couple of decades. And the reason is that it's possible to detect it in the spectra of quasar absorption lines, metal poor gas clouds in front of quasars. And, of course, the reason that's so good is that this material presumably is essentially unprocessed. It's left over from the Big Bang. And so you could just make these measurements, and you can figure out from that what the primordial deuterium is. The other great thing about deuterium is that we know it's not made in stars, so anything we see is going to be made in the Big Bang, and it's got a very sensitive dependence on the density of matter. That is to say, if you can pin the deuterium down, you get a really good handle on what the matter density is. And these are some recent measurements. This is late 2017. This is just from last January. And you can see that they're all more or less roughly consistent. They're all about 2.5 times 10 to the minus 5. This is the recommended particle data group value. And these are some other recent measurements. They're actually overlapping within 1 sigma, which is reassuring. Helium is a bit less well measured. The measurements of helium involve emission lines from metal poor H2 regions. And you not only measure the helium abundance, but then you have to extrapolate back because we know helium is made all over the place in stars. So the trick that people play is they measure the helium abundance in these metal poor regions, and then they graph it as a function of the oxygen abundance, and then they just try to do a linear fit down to a 0 oxygen abundance to get what we think the primordial abundance was. There's been a bit of a, what shall we say, an ongoing disagreement between the Isotov-Tuan group and the Skillman-Olive-Auer group. But you can see that they're not way out of line, but of course they don't agree to within their error bars. The particle data group, I think, believes these are more credible measurements, and I do too. But we'll see that even if you assume this, you're still going to get fairly wide range of helium produced. It doesn't let you constrain the baryon density as well. And finally, we get to the heart of this talk, which is the lithium abundance. So lithium abundance has been measured by Speed and Speet for many years now, starting in 1982 when they announced the existence of the Speet plateau. And what they discovered is that if you measure the abundances in metal-poor POP2 stars in our galaxy, and you confine your measurements to fairly low temperatures, but above about 6,000 degrees, these measurements all cluster around a single abundance, which has become known as the Speet plateau. Now, so the argument is that the Speet plateau actually represents the primordial abundance of the lithium. Now, the Speet plateau breaks down at various temperatures and abundances, and so at low temperatures, you start to see a decrease in the abundance below the plateau measurements. You also see a breakdown if you go to stars of very low metallicity, which is a little bit confusing. This is metallicity on the horizontal axis and abundance on the vertical axis. And you see there's a very nice plateau here. But when you get down to the very lowest metal, an Fe over H of less than -3, you also see this meltdown, which is not understood. But assuming that the Speet plateau is primordial, which we'll return to later in the talk, the lithium abundance is about 1.6 plus or minus 0.3 times 10 to the minus 10. And that's, of course, a very low abundance, but it's order of magnitude what you get out of Big Bang nucleosynthesis. Unfortunately, it's only order of magnitude. Other observations indicate that the lithium-6 fraction is very low compared to the lithium-7 fraction. Our own lithium-6 abundance on Earth is about 12%. So we have a lot more lithium-6. Lithium-6 is thought to be made almost exclusively in cosmic rays. So that's where our lithium-6 came from. But the observations indicate that there's a good upper bound on the lithium-6, and it's less than 5% of the lithium-7. So let's go back now and look at our abundance predictions from Big Bang nucleosynthesis and compare them to the observations. Now, this is a field in the 80s and 90s that was afflicted with a bit of triumphalism. People back then said Big Bang nucleosynthesis works, and anyone who disagrees with us is obviously an idiot. And I think that some of that turned out to be valid, and some of it, unfortunately, was invalid. What we've plotted here are on these yellow bands represent the observational limits. And so the horizontal bands are where the observational limits overlap with the predictions. And that means that the density predicted by helium, for example, has to lie somewhere between here and here. Now, what you'll notice is that helium does not put a very good bound on the baryon to photon ratio. It's a few times 10 to the minus 10 up to 10 to the minus 9. But the deuterium puts an amazingly good bound. The deuterium is this thin line here that you can barely see. And that puts a bound on the observed abundance that's centered around 6 times 10 to the minus 10. And the lithium, if you believe the lithium abundance is primordial, requires a baryon abundance between this bound and this bound. Now, in the days before the cosmic microwave background precision measurements, the game that people played was they simply took the observed abundances of the elements, they calculated ranges for the baryon density, they said, well, these overlap, the theory must be good, and we've got a nice measurement of the baryon to photon ratio. But of course, what has happened in the intervening decades is that the cosmic microwave background now gives you an incredibly precise measure of the baryon to photon ratio, which converts to the total baryon density in the universe, and it has essentially superseded Big Bang nucleosynthesis. I mean, some of my compatriots say, well, no, they're kind of equally valid, but they're not. Okay, the CMB is a much better way to measure the baryon to photon ratio. But what's interesting is that it agrees extremely well with nucleosynthesis. So the CMB limit is this vertical blue hatched line here, and you can see that it definitely overlaps helium. It puts the helium well inside the observed limits. It agrees it's an excellent agreement with the deuterium, and it's way out of whack with the lithium. It predicts a lithium abundance that's much higher than what we actually observe. So let's grade the elements and ask what grades they should get. I think that it's fairly clear that deuterium gets an A+. Okay? the deuterium measurements and the deuterium and predictions of Big Bang nucleosynthesis are in excellent agreement, assuming that we just begin with the CMB. Now, what about helium? Well, I know that they grade pretty easy at Harvard, so I'm going to give the helium an A minus, because you can't get a B. You have students at your door complaining. And that's not based on poor agreement. I mean, the agreement is actually excellent. It's just that the helium is so poorly constrained compared to the deuterium. But it's, I have every confidence that as the helium measurements get better and better, they're going to converge on this. And then what about lithium gets an F, I'm afraid. And the reason is that the predicted lithium from Big Bang nucleosynthesis, assuming the baryon to photon ratio from the CMB is about 3 times higher than the speed plateau value. So the theory predicts way more lithium than you actually observe, and this has been called the primordial lithium problem. That is, the Big Bang nucleosynthesis calculations yield 3 times as much lithium as the observed abundances. And it's a little misleading, as James Carville told Bill Clinton, it's actually the beryllium, stupid. And the reason is that in this regime, you're not producing lithium at all. You're actually producing beryllium-7. So in some sense, it's not the lithium problem. It's a beryllium-7 problem. And I say that as a theorist. Of course, from an observer's point of view, it's lithium. But from a theorist's point of view, what's happening is you're overproducing lithium. And that overproduced lithium, it turns you're overproducing beryllium in this regime. And that beryllium then decays into lithium-7 at late times and gives you too much lithium. So in that sense, it's really a beryllium problem. Now, let me take a second and dispel at least one other problem. For a while, we thought there was actually also a lithium-6 problem. There were measurements of the lithium-6 abundance around 2006 that seemed to show an observed abundance that's about 1,000 times the predicted abundance. Those are extremely difficult measurements to make. You're trying to separate out an isotope shift in the observations. And later measurements show no evidence of this. So if you read in the literature, you're going to see a reference to a lithium-6 problem and solutions to the lithium-6 problem. There's almost certainly no lithium-6 problem. So we don't have to worry about lithium-6. We're just going to worry about lithium-7. And then the question, of course, becomes, how do you solve the lithium problem? And there are 3 basic methods to do this. One is the astrophysics method. That is, there's something wrong with our observations. The speed plateau isn't really the primordial abundance. There's something else going on here, or the speeds have mismeasured it. That's the kind of the observations are wrong solution. Or not that they're wrong, but that there's other processes going on, and what they're seeing isn't the true primordial abundance. There's the nuclear physics possibility that our theoretical estimates out of Big Bang nucleosynthesis are way too high. That could be the case if we missed a reaction in the nuclear physics code, or if there was a resonance in some reaction that we were missing out on. So that's a valid possibility. And then the third possibility I will simply summarize as something weird is going on. That is, there's new physics in the early universe that is modifying standard Big Bang nucleosynthesis to give us different abundances than we expect. Now, before I go on and discuss all 3 of those, I wanted to mention a kind of weird factoid that is probably irrelevant, but it's kind of interesting. And that is, the beryllium-7 does not decay into lithium-7 right away. The lifetime of beryllium-7 is 53 days on the Earth, but it doesn't even decay after 53 days after Big Bang nucleosynthesis. And the reason is that beryllium-7 decays via capture of a bound electron. And there are no bound electrons in the early universe. Everything is ionized. And the rates for capture of just electrons in the plasma are way too small. It doesn't happen. So, in fact, Khatri and Sanyayev did a detailed calculation of this back in 2011, and they show that you don't really get conversion of beryllium-7 into lithium-7 until a redshift of about 30,000, which is when the beryllium-7 starts to recombine and become singly ionized. So it captures an electron at this redshift, and then it decays into lithium-7. And interestingly, it leaves a neutrino line. It emits a neutrino which gets redshifted to 860 keV today, which of course is totally unobservable, but maybe our distant ancestors will be able to see it with better technology. So what's weird is that this stuff is just sitting around as beryllium-7 for most of the age of the universe. I have not been able to come up with some method to exploit this and use it as a way to solve the lithium problem, but I know there are smarter people than I in the audience. So I simply throw this out as something to think about because it's an interesting curiosity, and we don't really know if there's a way to use it. So let me start off with, are the observational estimates too low? Well, first of all, there's always a possibility of systematic error. You need really precise measurements of the temperature to get these estimates right. But, I always get annoyed when theorists stand up and tell the observers that there's systematic error in their observations because my theory disagrees with your observation. So I'm not going to go down that road. I mean, that's just true of every observation, every experiment can always have systematic error. But, there's no obvious problem with the measurements. It's certainly possible that the primordial lithium got systematically destroyed. I mean, we know that stars can destroy lithium. What happens is there's convection. The lithium gets pulled from the surface down into higher temperature regions in the star where it gets destroyed. And that certainly happens in solar-like stars. There's convection there. It's expected to be a smaller effect in the low metallicity stars, but we know that it definitely happens because we see the meltdown. At very low metallicity, we're seeing less lithium. So something is destroying the lithium in these very low metal stars. But there's a couple counter-arguments that argue that this is not an explanation of what's going on. One is that the scatter in the plateau stars that we saw is exceptionally small. You would expect if there was lithium destruction, some of them be a little lower, some be a little higher. But it's really, really precise. I mean, it's almost a perfect straight line. And the other thing is that we don't see any metal poor spars above the speed plateau. You would think that if things got produced at the BBN level and got burned down to the speed plateau, there ought to be some stars you would see in between, or some stars way up at the top, and you don't see that. All you see at the speed, the speed metallicity and temperature is this one line of abundances, and you would think that you ought to see at least a few above that. So, yes, this is certainly a possibility that there's some kind of misalignment between the speed observation and the true primordial abundance, but there are arguments against that, and it doesn't look extremely likely. So let's go on to the nuclear physics then. Is something missing from our standard Big Bang nucleosynthesis calculations? These calculations have been refined over a period of, well, they started in 1967, so I was 8 years old when they began. And it's been nothing but improvement since then. And no one's ever made a huge mistake, and we've been improving and adding more nuclear reactions. So one possibility is that some reaction got left out or was mismeasured. Well, the most important reaction is helium-4 plus helium-3 gives you beryllium-7 plus a photon, because remember, we're overproducing beryllium. But this is extremely well measured. People have, of course, rechecked it because it's such a crucial reaction for the lithium problem. It's extremely well measured, and it's constrained by the solar model, because if you start mucking around with this, you start changing the solar neutrino output from what we measure that to be. So you can't just kind of reset this, and it seems like the measurements of it are pretty accurate. Another possibility that people were thinking of is maybe this reaction could be important. Beryllium-7 plus deuterium gives you proton plus helium-4 plus helium-4. That would destroy beryllium very effectively, and it was not included in the standard Big Bang nucleosynthesis code. But when the cross-section was measured, and by the way, we're providing work for all these nuclear guys at at Michigan State. I mean, they love us because you get to measure cross-sections, and it's important. But this cross-section was measured and found to be too small. It's not a big enough cross-section to actually effectively destroy beryllium-7. What about an unknown resonance? So, resonance is a especially strongly bound state at a particular energy. There's certainly a precedent for that, and that's the famous Fred Hoyle resonance. So Hoyle, of course, is famous for saying, in order to make carbon, you need this resonance. In order to make carbon in stars, you need a resonance that allows you to do a triple alpha reaction. Alpha plus alpha goes to carbon-12, and the resonance was duly measured after he proposed it. So it's a brilliant example of a theorist coming up with an idea that's actually correct. But the people have been looking for resonances, and you kind of know where they need to be and what level they need to be, and they haven't been found. Okay, so it's not like people are just saying, oh yeah, maybe there's a resonance out there. The resonances have been searched for, and people have not found resonances at the relevant energies in the relevant reactions. So it seems like this is probably not going to happen, and I would say at this point the nuclear solution is probably the least likely. There's been a lot of work in this. These are not experiments you have to do at the LHC. You can do them in your local they're not trivial to do, and you should never believe a theorist who tells you an experiment's easy to do, because I haven't done them. But these are things that people are constantly looking at, and there's lots of facilities where you can make these measurements, and they are being made, and we haven't found an obvious solution. So that brings me to the third part of the talk, which is, of course, the most important, and that is new physics. And again, I think that there's a legitimate complaint that as soon as a problem like this pops up, the cosmologists immediately jump on the wildest possibilities, but sometimes the wild possibilities turn out to be right. And the classic precedent for this, which happened in my lifetime, was the solar neutrino problem. So to remind you, Ray Davis built a solar neutrino detector down in the home state mine. He was looking for neutrinos hitting chlorine and forming argon, and he was going to test the standard solar model and verify it. And of course, what he found is that there were many fewer neutrinos coming out of the sun than the standard solar model predicted. And I remember having a talk. What year was that? It was I took a cosmology class at Princeton in 1979, taught by Ed Turner, and he presented this, and it was kind of like my talk now. He said, we don't understand this, and we don't know if the problem is with the standard solar model, or maybe something weird is going on. And of course, it would have been easy to modify the standard solar model, although John Bacall said, over my dead body, and it didn't happen. And he was simply refining the model better and better and better, and the prediction was pretty much, no, there should be more neutrinos there. And of course, the solution now, we believe, is neutrino oscillations, and not just any neutrino oscillations, but resonant neutrino oscillations in the matter in the sun that convert electron neutrinos, which you can see in these detectors, to mu and tau neutrinos, which you cannot see. And of course, that's been confirmed by other measurements of neutrino oscillations in the atmosphere. We know that the neutrinos mix, and that one kind of neutrino can turn into the other kind of neutrino. So the fact that sometimes the crazy ideas turn out to be the right ones, and it's especially true if you've eliminated everything else, right? The more you're kind of pushed into a corner, the more you want to consider unusual ideas. So what are some of the kinds of ideas that we've looked at? Well, one possibility is to destroy the beryllium-7 either during nucleosynthesis or a little bit later. This is not a paper about that, but Karsten Yudanzik wrote a paper called Did Something Decay, Evaporate, or Annihilate During Big Bang Nucleosynthesis? And that kind of summarizes the kinds of things people look at. You have a massive particle that decays, and the decay products can destroy the beryllium-7 or the lithium-7. Or you have something annihilate, and the annihilation products destroy the beryllium-7 or the lithium-7. But you have to be very careful with these kind of solutions, and the reason is that once you start mucking around with the lithium-7, it's very hard not to modify the other elements. And as we've seen, the deuterium, you pretty much can't change that at all. The deuterium is so tightly constrained now that if you bump it up even by 10%, it's going to be in violation of the observations. So you don't want to mess with the deuterium at all, and you've got a limited ability to mess with the helium-4. So anything you do to change the standard model of Big Bang nucleosynthesis had better leave those other elements more or less in place, and especially the deuterium. So a particularly good example of a failed idea that looked really good at one time is to inject neutrons in. So you can produce neutrons from the decay of other particles. You can have them produced from annihilation products. And neutrons really destroy beryllium-7 efficiently because they convert the beryllium-7 into lithium-7, and the lithium-7 hits a proton and fissions in half. That's why the lithium-7 abundance goes down at high densities. So this destroys lithium very efficiently, and there was a whole series of papers written showing that this was a way to solve the lithium problem. The problem with that is once you start injecting free neutrons, there's a lot of protons. Remember, the universe is 75% hydrogen. The neutrons bond with the protons and give you deuterium. And in a recent paper, Koch et al. Showed that pretty much any solution that destroys lithium this way overproduces deuterium. So this is pretty much out of the picture. You can't do this. It's not going to work. What about photons? Well, photons actually work pretty well. If you inject high-energy photons, this is an idea that goes back to David Lindley in the late 1970s. He was interested in fissioning other things, but if you have a particle that decays in the early universe and it makes a high-energy photon, the photon can come in and blast the nuclei apart. You could blast apart beryllium. You don't want to blast apart deuterium, but the binding energies of these things are really close together. If you get really energetic particles and you start dissociating helium-4, you're in real trouble because the helium-4 is hugely abundant and you then way overproduce deuterium. But what you want to do is somehow destroy this, but don't destroy that. Well, how do you do that? Well, you release a photon that's just a little bit above this energy, just a little bit below that energy. So Salvati et al. Wrote a paper last year where they had sterile neutrinos decaying into a lighter neutrino with a photon. The sterile neutrino mass has to be, and this is in the paper, they make a very precise prediction, between 4.18 and 4.48 MeV. And the lifetime has to be between 5 and 40 times 10 to the fourth seconds. This is the thing that has to be incredibly fine-tuned. So I actually talked to the referee of this paper, who's, I will not mention, I'll preserve his anonymity, although he told me he refereed it. And he said, yeah, it was really a crazy idea, but if the lithium problem wasn't such a bad problem, I'd reject it. But, we're desperate. So, he said, it works. You can't rule it out, and it makes a very precise prediction. So it's been published. Other kind of particle physics-oriented solutions, Pospelov suggested that if you had a negatively charged dark matter particle or some other kind of particle, it could bind to the beryllium-7 and lower the Coulomb barrier, making it easier to destroy. Or you could have an extra neutral particle which interacts directly with the beryllium-7 and destroys it, and those both work. Another possibility is to alter the cosmological parameters. So, for example, what if you have a baryon to photon ratio you measure at the time of Big Bang nucleosynthesis, you have another ratio that you measure at the time of recombination, but those could be different. If you dump photons into the universe between nucleosynthesis and recombination, you alter the baryon to photon ratio. The problem with that solution is that there's no region of consistency. Even if we threw out the CMB entirely, you can't make the deuterium consistent with the lithium by changing the baryon to photon ratio. So that solution really doesn't work at all. What about changing the expansion rate? Well, if you increase the expansion rate, for example, by dumping in extra relativistic particles at early times, it tends to increase the deuterium as well as decrease the lithium. But what if you could control the expansion rate at an arbitrary time and say it's normal, 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 oop, it increased a little bit, now it went back down to normal again. Even I'm not crazy enough to explore that idea, although I did actually explore that idea with the help of these graphs, and it doesn't work. So this is a paper, a very useful paper by Bambi et al., where they looked at how changing the expansion rate as a function of temperature changes the elements. And you can see that actually most of them are sensitive to the expansion rate over a pretty narrow range of temperatures. So the deuterium goes up sharply if you increase the expansion rate in this regime. Helium-3 we don't care about. Helium-4 always goes up. And the lithium-7 goes down. But the problem is, if you want to get the lithium-7 down, you have a fairly narrow range of expansion rates to mess with, and it totally overlaps the deuterium. And believe me, it doesn't work. I tried it. It's just not the right way to go. So finally, the last idea I want to mention, which gets into the paper I'm going to talk about at the end of the talk, is changing the constants of nature. Now, this is a long, an idea that goes back to Paul Dirac in the 1930s, and it was explored very carefully by Koch and his collaborators in 2007. It turns out that the biggest effect is changing the binding energy of deuterium. And oddly enough, if you increase the binding energy of deuterium, you decrease the primordial abundance. It's completely opposite of what you'd expect. The reason is that if you increase the binding energy of deuterium, nucleosynthesis can start earlier because the deuterium is more stable, and then more of the deuterium gets burned into heavier things. So it's counterintuitive. And if you do that, you can actually get a regime where you change the lithium and the deuterium and barely make them overlap. Now, the idea that I want to talk about is a paper, this is Scherrer and Scherrer, because I thought, there's a speed and speed, so there ought to be a Scherrer and Scherrer. And that's what happens if you have stable beryllium-8 in the early universe. And this was inspired by a paper by Fred Adams and his postdoc in 2017. They were trying to make an anti-anthropic argument. So you know there's this famous argument that the resonance, the famous Hoyle resonance, represents a fine-tuning in the universe. And if that fine-tuning weren't present, life couldn't exist. And so they said, well, imagine that the resonance wasn't there, but that the binding energy of beryllium was different. Because you could certainly imagine that. You could change where the resonances are. And they showed that if you have stable beryllium-8, you can make all the heavier elements that you want. Not only that, but you don't have to change the constants of nature very much in the early universe to stabilize it, because it's almost bound. It's got a binding energy of negative 0.1 MeV. So it's like a 10% change in the quark masses or the strong force in the early universe makes beryllium-8 stable. Now that was the motivation for our study, because what we really wanted to do was just see what happens. We weren't particularly interested in solving the lithium problem. But after I posted the paper, I cross-listed it to nuclear theory, which I've never done before, nuclear theory on the archive. And immediately a nuclear theorist emailed me, and he said, besides, could you cite my paper? He also said, I actually have a relevant paper, and it was relevant. What Yao and Bernd Mueller down in North Carolina showed was that they argued that plasma effects in the early universe might stabilize beryllium-8 at early times without the need for any beyond the standard model physics. So what we did in our study was we took a standard Big Bang nucleosynthesis code. We took the binding energy of beryllium to spontaneous fission to be a free parameter, B8, and just calculated the abundance as a function of B8. We took the cross-section. This cross-section has actually been estimated because it comes up in various nuclear processes in stars. The estimates differ a bit, so instead of using one of the three, we simply parametrized the cross-section in a standard way, taking this constant in front also to be a free parameter. But then we can compare the value of this for interesting effects with the typical values of these measurements that it corresponds to. So we've got a two-parameter model, and let me show you what happens. Here's abundance of helium and beryllium-8 as a function of this binding energy. This is fixing the baryon density to be the CMB value. And what you can see is that in the standard model, you make no beryllium-8, and you make helium at the standard amount. But as you increase the binding energy of beryllium-8, more and more of the helium gets bound into beryllium-8, and so you end up with almost no helium and almost all beryllium-8. Now, the first thing you should say is, well, the model's wrong then, because we don't see any beryllium-8 today. But remember that whatever is causing the beryllium-8 to be stable in the early universe is not going to be around today. So at some point, either the screening effect is going to go away, or the constants of nature assume their current value, and this thing simply spontaneously fissions back into helium. And the sum of these is constant, which means that the helium abundance is completely unaffected by this process. You bind into helium, into beryllium-8, you fission at late times, but you don't change anything else. The helium is the same. We also see no change in the deuterium abundance either. The deuterium is completely unaffected by this process. We don't see any buildup into heavier elements. This was also investigated by Cook et al. In 2012. So there's no production of heavier elements like carbon. And one corollary of this is that there's a famous statement that there's a mass gap at A equals 5 and A equals 8, and that's why you don't make heavy elements in the early universe. This is not true. And they make this point, they made this point 6 years ago, and I'll restate it here. The reason you don't make heavy elements in the early universe is that the Coulomb barriers are too high, and the time you have is too small. So it has nothing to do with whether there's a mass gap or not. So far, this doesn't change anything in the standard model. It doesn't change the beryllium-8 just disappears, the helium stays the same, the deuterium stays the same. But what does change is the lithium-7 abundance. The lithium-7 abundance actually goes down as the binding energy of the beryllium-8 goes up. And the reason for that is that in the early universe, you're binding the helium temporarily in the form of beryllium-8, so it's sort of sequestered, and it's not around to get burned into beryllium-7. So it's kind of held prisoner in the beryllium-8, that at late times it fissions, and you can't make more helium. And so what you discover, by the way, the measured values of the reaction rate are around this red line here. So you can see that for binding energies of between 2 and 3 MeV, you can easily get a lithium abundance that falls within the measured range. Now, what are the pros and cons of this model? Well, the pros are that you can reduce the primordial lithium, but leave all the other element abundances completely unaffected, which is the holy grail of this field, right? You don't want to make too much deuterium. You don't want to modify the helium too much, so that you can actually do that with this model. And the required fusion cross-section for beryllium-8 plus beryllium-8 is completely reasonable. It's about what the people who've measured it need, what they have suggested as a reasonable, not measured it, but estimated it using nuclear theory calculations. You can't measure it because it doesn't occur in nature. The cons are we've neglected, if you believe that this is due to either screening or it's due to changing the fundamental constants of nature, we haven't considered changes in the other nuclear binding energies. The binding energy you need for stable deuterium is about 1 to 3 MeV. You can easily accommodate that if you change the constants of nature, but it's hard to achieve with screening, with the nuclear screening. The kind of binding energies the nuclear theorists are getting are much below this. They're positive, but they're less than 1 to 3 MeV. And then, of course, the other problem with it is, as they say, admittedly speculative. Okay, it's not your mainstream solution. So, where should you put your money now? I'm going to paraphrase a paper that Avi Loeb wrote. He was comparing, different research areas you could work on, the more speculative versus the more standard, to a portfolio of investments. And he said you shouldn't put all your money in the crazy stuff, but you shouldn't put all your money in the boring stuff either. You need to be sort of in between. So where would you invest your money? Well, I would put the astrophysical solution at about 80% likelihood. It's like money in the bank. In fact, it's exactly like money in the bank because you don't get much return on that. But I think most people in the community think it's likely an astrophysical solution. It's just they have no idea what it is, right? We don't know. But astrophysics is messy. It's not like terrestrial physics where you have strong control over the experiment. So they think there's something lurking out there we've just missed or don't understand. I think the nuclear physics solution is more like junk bonds at this point. It's very, very unlikely something's hidden there that we haven't seen. It's almost certainly, this has been run to death. Now, I didn't put it to 0 because it hasn't been run totally to death. But it would be very surprising in my mind if we discovered a new resonance or a mismeasured cross-section that we hadn't been thinking of. And then for the new physics, and I don't mean my paper specifically, but just the general idea of new physics, I'll put that at 15%. That's the high-risk, high-reward area, where if it turns out to be true, of course, you could, if not win the Nobel Prize, at least get elected to the National Academy. Given last week's stock market, you might not want to be putting most of your money in this. You might want to put more in this. But I would put these as the likelihoods at this point of these various solutions. I did want to mention the pharmaceuticals. So there's an interesting issue which I have not been able to run to ground, but people have investigated or tried to investigate whether the isotope of lithium makes a difference in the response of the brain to these antidepressants. And there were some experiments on rats in the 1980s which suggested, in fact, that there was a difference between lithium-6 and lithium-7 in the brain. So that's an interesting relation between, if all the lithium-7 was made in the Big Bang and the lithium-6 is made in cosmic rays, it's an interesting relation between our brains and the early universe. But since we don't really know any of that stuff for sure, I'll leave it at that. Thank you.
Okay, questions for our speaker? I have two.
Okay.
So I'll ask one and then go back to the audience for a second. You talked about plasma effects stabilizing the beryllium-8. Can you give me an intuition for what the
Well, I think that the hand wavy explanation is that you have the beryllium-8 and the beryllium-8, and you have two heliums, and they want to come together to fuse and make beryllium-8. And they can't do it. There's a Coulomb barrier there. But if you stick a bunch of electrons in between, it tends to cancel out the Coulomb barrier, and then it makes them more stable when they come together. Okay. And then the non-intuitive explanation is many Feynman diagrams and horrible equations.
Squiggly lines.
Yeah,
Right,
squiggly
right,
lines,
right,
yeah.
Got it. All right, and my second question, you put 80% of your money on astrophysical
Right.
guess, which at the beginning you said meant the observations are wrong. So I've heard that if you want to sound really smart in a talk, you ask about the effects of dust or magnetic fields.
Yeah.
Right. So what are we going to blame this one on? Is it
Well, it
magnetic
doesn't.
fields
It doesn't
or-
necessarily. I mean, I should say there's really two. There's two components to the astrophysical thing that I've kind of elided in the talk. There's that they're measuring the wrong abundance in the speed plateau. That there is a speed plateau, but it's just they somehow mismeasured it. That would be the systematic effects or the magnetic fields or the dust. The other possibility is yes, the speed plateau is real, but for some reason it doesn't represent the primordial value. That it could have been destroyed or created and then given you the speed plateau. So it's really the first of those you're asking about, and magnetic fields are the last refuge of a scoundrel. I really don't know. I have no idea how if you could make that work. And the speeds are careful observers, and I'm not either careful or an observer. So I tend to trust their measurements. I think it's more likely that the speed plateau just doesn't represent the primordial abundance than that it's been mismeasured.
So with your 15%, I mean, what would be the experiment you want to build to prove or disprove your...
Well, the guy at North Carolina said you could measure the effect of electron screening in laboratory experiments, so that would be number one. I mean, that would be, the question is, we've been bouncing around with dark matter out there for decades now without seeing it. I think it's about time somebody saw it. Don't you? Yeah.
Sure.
So there was a lot of excitement several years ago about lithium-6, as you said,
Mm-hmm.
And you're saying that went away. So, I mean, obviously the abundance is very low, but
Yeah.
other than that, why is it so hard? I mean, is it worth...
Well, you mean it's hard because you're measuring these two lines. It's isotope shift. So there's one line that's buried in the wings of the other line, and that's why it's so. I mean, yeah, it'd be worth knowing that number. I mean, then you're going to again face the problem of even when you have the abundance, are you going to know that it's the primordial abundance? So I think it's that was a huge discrepancy. That was like 4 orders of magnitude discrepancy between what BBN predicts and what they were arguing is maybe observations. But yeah, it's a measurement worth knowing. And I say that as someone who's not going to be spending nights at the telescope looking for it, but I think it hasn't been resolved what the real abundance is. It's very difficult.
I saw one other question over here. Are there any other questions? All right, let's think about
Okay,
one more.
thank you. Yeah. No, thank you.
What can I help you with?
Nothing, because I've got this. I'm supposed to meet somebody at 3, I think. Oh, the microphone, yeah. Yeah.
Sure where this goes, but
Yeah.
thank you.
Okay, so just to be clear, we don't have a dinner thing. I just eat with my son.
That's correct.
Okay, so I should talk to him. Dinner is on us. We can just go where we want, and I'll get my dinner paid for. So pick out someplace. Well, let's just meet somewhere. So I'm meeting with people. Let's see, what is it now? It's 3 o'clock. I think I'm meeting with people till 4 o'clock. So why don't you want to meet around 4? Are you going to just hang out here in the library
Yeah,
or
we're just
something?
gonna hang out until dinner. We'll probably get some work done.
Well, where are you going to be?
Are you gonna be around here?
Yeah.
Okay, I'll probably just be around here then.
Well, I know, but we should probably. I mean, you're counting on the cell phone to join us up. All right. Well, if you don't find me, I'm up on the 2nd floor in one of the offices up there.
213
It's
or
the office.
260?
It's right next to the director's office,
Okay,
and I'll keep the door open. So just bang on every door next to the director's office.
that's good.
All right. Did you enjoy the talk?
I did actually.
All right.
I understood little of it, but
Enough. All right.
it made the way you presented it allowed me to kind of participate. And now I know not to prescribe the right isotope of lithium.
All right. Well,
to my future
take
patients.
that. That could be your PhD dissertation.
There you go.
All right.
What else can I help you with?
Well, I just need to go back and find the next person I need.
Okay.
Are there any like lounge areas around here?
Dark matter yet?
I can write you that. Yeah, follow me.
You're around on the tussle. Sorry. Oh, no. The stars don't line that up, but this is magic. Like, well, I have to email them. I was like, hey, you're here. It's nice.
Yeah. So, good. How are you doing? So where
stars align.
I was
It's
just,
not, I could not figure out how to do that.
Well,
I could
work-
change
well,
channels.
I'm bouncing around. So
You
I
can
work
change
for-
channels.
No,
change the channel.
Change the channel. I was just imagining broadcasting to another classroom or something.
This thing.
You know, I'll just check with Mark.
I was